Chapter 9 Electrolyte Solutions, Section 9.3 Activities of Solvated Ions. The chemical potential of an electrolyte in an aqueous solution is the sum of the chemical potentials of both the cations and the anions. Therefore, this chemical potential of electrolyte is equal to the chemical potential of the cations plus the chemical potential of the anions. Over here, nu plus and nu minus are the coefficients of the cations and anions in the ionic formula. For example, if we have aluminum sulfate, in one such unit we have 2 aluminum cation and 3 sulfate anions. Therefore, the chemical potential of aluminum sulfate in water is equal to 2 times the chemical potential of aluminum 3 plus and 3 times the chemical potential of sulfate. There is no way to separate the cations from the anions in an aqueous solution. Well, in the solution, the total charge has to be balanced, and therefore we'll have to look at the chemical potential of both ions simultaneously. Now let's look at the arithmetic mean ionic chemical potential. We define this to be nu plus minus. Nu sub plus minus is equal to, now you can see we're doing the average here. We have nu plus mu plus and nu minus mu minus on top. That's the total chemical potential of all ions, including cations on the left, anions on the right. On the bottom we have coefficients. It's nu plus plus nu minus, and overall we have this nu equals nu plus plus nu minus, and we have this arithmetic mean ionic chemical potential, again denoted by mu sub plus minus. For aluminum sulfate, here's the example. Its arithmetic mean ionic chemical potential mu sub plus minus is this. We have 2 times the chemical potential of aluminum 3 plus and 3 times the chemical potential of sulfate divided by 5, because in 1 unit of aluminum sulfate we have 5 ions, 2 aluminum cations and 3 sulfate. So we're just taking the average over here. Mu plus minus is equal to 0.4 or 40% of the chemical potential of aluminum 3 plus and 0.6 or 60% of the chemical potential of sulfate. And in general we have this equation again. Mu sub plus minus is the arithmetic mean ionic chemical potential. It's equal to the average of the chemical potentials of the cations and anions altogether over here. And in this equation we simply added this superscript naught to denote the standard state. So we're going from a more general equation to a more specific equation under the standard state. Now let's look at the difference between this mu sub plus minus and mu naught plus minus. The difference is expressed here. This is the equation for this mean ionic chemical potential, and this is the standard mean ionic potential. So we have this equation. We combine this cations here, we combine the anions here, and now we set the difference between this and this to be RT times the natural logarithm of A plus. Again, mu plus is equal to mu plus naught plus RT times the natural logarithm of the activity of the cation. And over here similarly, mu sub minus minus the standard mu sub minus is RT times the natural logarithm of the activity of the anion. So we have this equation now, and we have RT in the front, and then we have the sum of 2 logarithms that becomes a product inside, and then we have a division here. It becomes this 1 over nu as the power of this term. Now we have a new concept over here. This A plus minus is the so-called mean ionic activity. Again, this A sub plus minus denotes the mean ionic activity. So it's defined as this. This is a geometric mean of the activities of cations and anions. So this is A plus, the activity of the cation raised to the power of nu plus, which is its coefficient in the ionic formula. And this is A minus, the activity of the anion raised to the power of nu minus. Nu minus is the coefficient of the anion in the ionic formula. And then we have the whole thing, the product, raised to the power of 1 over nu. Again, this is so-called the geometric mean of the activities of these ions. And this nu is the sum of nu sub plus and nu sub minus. And now we have this equation. Over here we have the non-standard arithmetic mean ionic chemical potential. This is the standard arithmetic mean of the ionic chemical potential, and then the difference is RT times the natural logarithm of this geometric mean of activity. Now, given the mean molality and mean activity coefficients of the ion, we can calculate the mean ionic activity. Well, it's just because of the definition over here. So we just define the activity of ions to be the molality divided by m naught and then multiplied by a coefficient. This coefficient is the so-called mean activity coefficient. And this mean activity coefficient is simply the molality without the unit. So the molality divided by m naught and then divided by this activity. That's the definition of the mean activity coefficient. So now let's look at the mean molality. It's a geometric mean. So m sub plus minus is over here. You can see this is a product of the cations and anions. This is the molality of the cation to the power of nu plus, and this is the molality of the anions to the power of nu minus. And altogether raised to the power of 1 over nu, and nu is the sum of nu sub plus and nu sub minus. Now let's look at one example to better understand this equation. For aluminum sulfate, we have m sub plus minus equals the molality of aluminum cation raised to the power of 2 and the molality of sulfate raised to the power of 3, and altogether raised to the power of 1/5. So we have this similar equation over here. For the mean activity coefficient, gamma is the activity coefficient, gamma plus minus is the mean ionic activity coefficient. It's gamma of aluminum 3 plus to the power of 2 times gamma of the sulfate to the power of 3, and then altogether raised to the power of 1/5. Again, we see 2 here, 3 here, because in one ionic formula we have 2 aluminum ions and 3 sulfate ions. Now let's look at the mean activity. Again, A sub plus minus, it's the activity of aluminum 3 plus squared times the activity of sulfate to the power of 3, and then raised to the power of 1/5. We can actually separate this A into m multiplied by gamma. So this is actually each A is I think we have over here, each A is mostly just m times gamma, and divided by m naught is to remove the unit in the molality. That's 1, and 2, we're using m naught as the hypothetical standard state right here. We just compare all other concentrations with this standard state. So over here we have a new equation. You can see this is m plus minus. So over here this is the mean molality, and over here this is the mean activity coefficient, divided by m naught, again for 2 reasons. One is to remove the unit in the activity, because eventually we need to take the logarithm of the activity, and it does not make any sense if you take the logarithm of something with a unit. So what's the logarithm of mole per gram? I mean, it does not make any sense. So right here we can remove the unit, and also there's another reason. Hypothetically, we use this M0 as a standard state for the ions. You'll see that later. Again, the mean ionic activity A plus minus must be unitless.